How to find multiple roots. What we know is that if there is a multiple zero or a multiple root, then the derivative will have that same root and of 1 degree less. Let's prove that. So what we're saying is we've got some polynomial and there's a 0 which is a multiple root, so it'll have a linear factor to some power, let's say m, times some other polynomial, but that other polynomial wouldn't have a as a root, because otherwise that would change the multiplicity or the order of that particular root. Well, if we differentiate that, so using a product rule, and so write down the first, diff the second, plus write down the second, diff the first, and we can factorise that, and we see, yes, we can pull out a common factor of x minus a to the power of m minus 1. So its multiplicity is 1 less. All we now have to confirm is that a is not a solution to this other factor, otherwise that will change the order. If we look at that other one, we know that when we substitute it into the first part, that's going to be 0, because obviously a minus a. Is a solution to mqx? Well, no, it's not, because up here we defined it and said a is not a solution to qx. So it would be impossible to factorise out another x minus a out of that second parentheses. So that proves our result. Okay, well that's handy, because if we know something has a double zero or a triple zero or whatever, or we want to investigate, we can look at the derivative. Now here's a cubic, and we're told it does have a double root. Okay? It has one. Go and solve it. Alright, well that's a cubic. Heck of a lot easier to solve a quadratic than it is a cubic. And I know one of the solutions of this quadratic must also be a solution to the original polynomial, because it has a double root. Well, that gives us two possibilities. It's either minus 1/3 or 3. And you want to pick logical ones, and I mean I could be wrong, but I think minus 1/3 is not likely, because if it was a solution then I would expect to see 3x plus 1 as a factor in the polynomial. My original polynomial is monic. Okay, I suppose I could make it, 3x plus 1 by multiplying everything by 3, because it's an equation. But that's what I'm saying, it's just not likely. I'm going to check the other one. That's the more likely scenario, that it's x equals 3. If we sub that in, yeah, it does work. So I know x minus 3 squared is a factor, and it's then just a matter of working out the other linear factor, which turns out to be x plus 2. And so now we solve it. X is -2 or x is 3. I like this one because it was in 1991, which if you think about it, that's symmetric or palindromic, and the actual polynomial they gave us was also palindromic. It fit nicely. I don't know if they did that on purpose, but there you go. So the polynomial x to the power 4 plus ax cubed plus bx squared plus ax plus 1, alpha is a solution, and they've given us this interesting fact that 2 plus b squared cannot equal 4a squared. Okay, I'm sure that will become useful. We have to show that alpha can't be 0, 1 or -1. There's no way these three could be a solution to this polynomial. Well, 0 is easy to pick, because if you sub 0 in, clearly you're going to be left with 1. So alright, 0 can't be a solution. Polynomial 1, we get 2a plus b plus 2. We don't know what a and b are. We got this interesting relationship, but alright, let's look at -1. And now that's where this interesting relationship comes in handy, because look at what we've got. For polynomial 1 to be a root, 2a plus b plus 2 must equal 0. And for polynomial -1 to be a root, well, -2a plus b plus 2 equals 0. But there's the fact they gave us. 2 plus b squared can't equal 4a squared. Therefore, 2 plus b could not be plus or minus 2a. Move that to the other side and you'll see we've got these two conditions. Plus 2a plus b plus 2 can't equal 0, therefore 1's not a root. Minus 2a plus b plus 2 can't equal 0, therefore -1 can't be a root either. Now we're going to show that the reciprocal of alpha must be a root. Well, if I substitute it in, I get this expression. Algebraic fraction, let's put alpha to the power of 4 as our denominator, and the top of the fraction we get 1 plus a alpha plus b alpha squared plus a alpha cubed plus a to the power of 4. But that is polynomial alpha, and that's because those coefficients were palindromic or symmetric. So we've got the same thing, and we know alpha is a root. So polynomial alpha is 0. It's a polynomial. 1 on alpha is also 0. Therefore, yes, 1 on alpha is also a root. And that result is always true when the coefficients are palindromic or symmetric. All right, step further. If it turns out that alpha is actually a multiple root, then its multiplicity has to be 2. There is no other choice. And further to that, 4b has to equal 8 plus a squared. Well, we just said if alpha is a root, so is 1 on alpha. So every time we see alpha, we see 1 on alpha. But if we're saying alpha is a multiple root, then so must 1 on alpha. Because every time we see alpha, we see 1 on alpha. Well, if it's a double root, let's say it's a double root, then 1 on alpha would also be a double root. And there's 4 roots. But this is a quartic. And a quartic can't have more than 4 roots. Well, therefore, you can't have multiplicity of more than 2 then. So if it has got a multiple root, it's got to be a double root. It can't be anything else. We also have to prove this thing. 4b is equal to 8 plus a squared. But now we know the double root situation. So let's find the derivative. There it is. The roots of this derivative are going to be alpha, because it was a double root, 1 on alpha, because it's a double root, and there'll be a third one. Let's just call it beta. Let's play around with it. Some of the roots 1 at a time. That's what I get. Some of the roots 2 at a time. And then some of the roots 3 at a time. Let's play around with these. Basically, I want to eliminate alphas and betas and end up with that expression. So if I substitute the third one into the first one, I'll end up with this. Alpha plus 1 on alpha, so the beta is gone, is equal to minus a half a. If I now substitute that third one into the second one, and this is what I get. But hang on, I can factorise that first line. I get alpha plus 1 on alpha, which we showed was minus a half alpha. That gets rid of the alphas. I now have an expression with just capital A and capital B, rearrange it, and I can get the expression they want. 8 plus a squared is 4b. So 10g and 10h, just put a little note here, that if a tangent to a cubic has 2 solutions only, then what would happen? There we go. So I've got a tangent to a cubic, so it ends up with 2 solutions. The double root must be there, where the tangent hits.